This is GS Database Systems 1, Module 6 lecture, where we'll talk about set operators, normalization, and advanced modeling. I'm instructor Robert Hewlett, and you can contact me via Gmail or Twitter. The general learning outcome is to master, know, and understand all the content and concepts discussed in the lab, lecture, and the assigned readings. Specific learning outcomes, although not an absolute list: distinguish relational set operators, define and apply normalization, define and apply the first normal form, define and apply the second normal form, define and apply the third normal form, define and apply Boyce-Codd normal form. Discuss some advanced modeling concepts such as subtypes. Discuss possible hazards when normalizing data such as fan traps, chasms, and redundant relationships. First, I want to talk about relational set operators. Relational set operators allow us to interact with multiple tables at the same time. We can union two tables together, union and union all. So union combines all the rows from one query or table with all the rows from another table or query. If we don't use the all option, any duplicates only show up once. The all version allows duplicates, or however many times the row combination might repeat, shows up in the result. So union will have one version. So say you have in the output from union several queries together, 5 rows that all have the same values. If you just use the regular union, only one row will show up. If you go all, then all the rows will show up, right? So duplicate rows. That means that every value in every column has to be the same. Intersect returns rows that appear in both, so that appear or are common to both the queries or both the tables that you're querying from. Except is very similar to difference and minus you might find in other software. The official word is except. So return the rows that appear in the first query but not the second. So it's almost like subtracting one table from the other or one query from the other. You can learn more about these relational set operators via the link below. So here's an example of how a union would look. Select star from names 1. And these tables are in a database in our cluster. So select star from names 1, union select star from names 2. And here I'm going to order by ID. Now the idea is that here, if there's a duplicate row or a triplicate, right, or only one row shows up in the output. Sort of like select distinct. Select star from names union all select star from names 2 means that all the rows are going to show up from both queries regardless of duplicates, right? So if you have the same if you have some rows that have exactly the same column values and it shows up 10 times, then it's going to show up 10 times with union all. Select star from names 1 intersects select star from names 2. So only where the rows that are in common, right, from both queries or tables will show up in the result. Okay, so they have to be the same in both tables, and that shows up in the result. Select star from tables names 1, except select star from names 2 would basically, any rows that are in common, right, are actually removed from the result. So if there are 2 rows in names 2 that also exist in names 1, they won't show up in the query. So it's almost like subtract. What you can do now is pause this video lecture and watch the demo where we'll actually write SQL in the database and we can see the rows that come back. So what I want to do now is just review the design process just to get our feet sort of set. So typically we start off by identifying the entities, and we do that by working with the end user in order to understand, well, one, their data, how they work with it, how it's used in their workflow, and what questions they want their data to answer. We group the data into logical entities or objects, and we determine the entity's attributes. What exactly do you want to track for a particular entity? We also define relationships between entities. Now, one thing is don't force it. If the relationship is not there, it's not there. We also try to ensure that the tables are in third normal form, and we'll talk about the normal form shortly. Often this can expose hidden entities, that there's actually two things being tracked in the table, and typically we want an individual table to track one thing, one noun, one entity. The relationships can typically have the following cardinalities in a relational database: one to many, many to one to one, and many to many. And in a relational database management system, a many-to-many relationship is special in that it needs another table in the database to actually resolve it. Here's an example of a Curtis model that was used during my time in government. And so we had all these relationships between companies and tenures had sites, and at a particular site an activity was being done, and we had a usage level. But when we first did this, we took a relational approach. We actually introduced something called the fan trap that we'll talk about later. And it took us, and we need to actually reorganize the data to make sure that it was bringing back the proper result. And so you can go through this process and actually, cause a problem. And again, first we have to go through the process, and then we'll bring up some of the problems that you can create, and you have to be sort of vigilant for. So the problem. So why do normalization if it can cause an issue, right? So how we on a regular basis look at data, or how we view data, is often one big table. So there's lots of people who use like an Excel workbook or something like that to manage some data. And it's not bad. It's better than using paper, and it's better than a Word document because they're kind of structuring it into rows and columns, and that helps. But there aren't a lot of constraints in Excel. And if we're going to use Excel to do it and only use one workbook, then we have to denormalize the data or not doing it in a normal form. And this can cause problems, right? Although the end user does love it, there are problems. There can be a lot of redundant data. And so it can require many updates on many columns to get a value changed, right? And because it can get, you can miss one here and there, your data gets out of sync, or what we call inconsistent. Also in this denormalized or flattened structure, the data can be hard to analyze. So we're just going to take a look at a MinFile examples. This is like a mineral data that you can get from the government, and it usually comes in this denormalized flattened structure. And the thing is, when we look at the data, one thing that tells us there's a problem is if there's a lot of repetition. And so there's lots of examples in here. We have to follow it a very structured sort of way of working through the issues. One of the first or primary things we have to solve, and we'll talk about this in normal form, is that although we can see zeros repeating here, and we can see blanks repeating here, and we can see words repeating here, what's an even more important issue is the fact that the column names kind of repeating. Quantity 3, quantity 4, quantity 5, quantity 6, commodity 1, commodity 2, commodity 3, commodity 4, commodity description 1 is commodity description 2, commodity description 3. So there's a lot of repetition, right? So we have repetition with this set of columns. There's even, I'm only showing a partial view here, but there's a quantity 1 and 2 to the left of this. We have more with just the 2-letter commodity codes, more with the commodity description. So a lot of repetition. We also have the other values like 0, although 5 is there, but a big block of that is zeros. And what that really means in this database is that they're There is no quantity 6, quantity 7, or quantity 8. It's actually null. But because it came from a different system, or the interchange format doesn't understand what a null is, a bunch of zeros get filled in. And we also have this issue here where there's a whole bunch of blanks, right? And it's not that there's a seventh commodity and they don't know what it is. It's just that they weren't mining 7 different minerals at this particular site. But a blank shows up because of this flattened structure. So the solution, what's the solution? So we need to change how we view data. So we can structure or reorganize the data in a way that we minimize redundancy and ensure data dependencies. So basically making sure that all the columns are synced to the primary key so that when it changes, they change. There are some benefits to doing this. You save a little bit of disk space, right? You increase efficiency when managing the data. You remove, insert, update, and delete anomalies. And you increase data consistency. And this is huge because if you trust your data, then you'll trust the analysis or numbers that result from analyzing that data. So there's a process called normalization. It's a process we apply to the entities in the yard diagram, so the tables, to make sure that there are no hidden entities. So that typically means 2 or more entities in the same table. As soon as that happens, we have problems. In the previous example where we had repeating column names and we had a lot of zeros and a lot of blanks, it's typically because we're trying to do a one-to-many or a many-to-many in one table, and that starts to cause ourselves problems, right? So if we do find hidden entities, it's not a big deal. We just need to create new tables to put them into, right? And then we have to figure out, is that a one-to-one or was that a one-to-many, many-to-one, many-to-many relationship that we were able to pull apart. So we'll start with first normal form. Data should be atomic. Now this part about atomic sometimes gets lost. People jump right to repeating groups, and we should actually start with the whole concept of atomic first. So what to look for is the repeating groups, right? Repeating column names is what people talk about. And what that typically means, it's a one-to-many or a many-to-many that's going on in one table. So in the previous example, we had quantity 1, quantity 2, quantity 3. Then we had description 1, description 2, description 3. I think it was all the way up to 6, right? And code 1 all the way up to 6. And so we see this a lot. It's not, fortunately or unfortunately, it's not unusual. Even in forest cover or VIR data, it's called now, vegetation resource data. So you'll see species 1, species 2, species 3, species 4, species 5, species 6, right? Because what they're tracking up for a particular forest stand are up to 6 different species in that stand. And the question really is, or a question is, does the 1, 2, 3, 4, 5, 6 mean something? In some cases it does. So the 1 means the most dominant species in that stand. Very important information you might want to analyze, and it's buried up in a column name. So that's why restructuring the data actually helps, because we can do more sophisticated queries and ask better questions if that 1 is actually a row value that we can select on a where clause. So typically these must be removed, and we do that by spinning out off another table, and then we're going to figure out, in this case it's a one-to-many in this example. All right. A bigger issue is probably columns that contain several data types. So let's say the following address information was stuffed into one column, right? So 3700 Wellington Avenue, Burnaby, British Columbia, Canada. Then V5G, 3H2, and then 604 434 5734. Now there's a whole bunch of different things and concepts stored in that one address, right? So a location on a street, a particular street, Willingdon, and then a classification, Avenue, Street, Crescent Place. We've seen that, which, Burnaby's a city, cities table. British Columbia is a province, province table. Canada's country, country table. Postal codes, right? And then phone numbers, which can be further decomposed as well. Also, multi-value attributes. Again, is instead of a one-to-many using repeating column names, we do a one-to-many right in one column, right? So you might see a list of values separated by a comma or a semicolon right in the table. Always be concerned with alphanumeric codes, right? They're usually a combination of values that can be torn apart. But you have to be a realist about how far you intend to go, right? And simple is always best. It might be more accurate to rip the code apart and that. So a big thing on TRIM is terrestrial resource inventory mapping data. So all your planimetric data, contours and rivers and that, all those features have feature codes. And so DA means, it's still stuck in my head, it means it's some type of road, right? And so so those codes are usually contain a lot more information, right? Here, to go with the mining data that we looked at before, right? Their primary key 082ENE001. So one, I know that 082 gets me on a certain block. E gets me within a hierarchical block, smaller block inside that. NE means the northeast corner, further spatially putting me into a particular area in the map. And then 001 would be the first mine site, where someone registered a claim in that area on the map. So there's a lot of stuff going on there. So do you break that code down into its 1, 2, 3, 4 parts or not, right? Because there's usually 4 parts to that one code. And so you just gotta, how far do you go, right? Are you a purist? Then you have to break that apart. And if you have some common sense, and that changes depending who you talk to, you keep it together because that's a unique identifier. Just to talk about, your postal codes, there is a hierarchical spatial breakdown in the code, right? So K definitely, in this example, K1A, the very first letter typically does get you to a province, or in the case of a really big province like Ontario, a certain part of that province. So the forward sort area or sortation area, does break you down. That code itself, breaks you down hierarchically, spatially. So it typically gets you to, province, territory, and then down from there with the first letter, and then the number would get you to an area within that, and then the letter A would get you to an area within that, right? And then the local delivery area, again, also can be broken down. So are you going to break that postal code into 6 columns, right? A lot of people don't. Some people break it into 2, right? So how far will you take that, right? And that's usually a personal time decision. Second normal form assumes that your table is passed all these first normal form tests, no repeating groups, data is atomic, all that kind of stuff. And so second normal form is a very special case, so remove functional dependencies on parts of a composite key. And that's really important, composite key. Okay? It means you don't have a single column as the primary key. You need to have multiple columns. So you can have more than 2, but as we talk here, we'll just use 2. So what you find is when the primary key changes, certain columns do change, but others do not. And when you change the other part of the key, then this other series of columns change, and the other ones stop changing. And so what it means is you're partially dependent on the primary key. Not fully, you want full dependency, right? So when the primary key changes, because it's supposed to be in charge, all the other column values are changing. But if you're noticing that when I change, say, part 1 of the key, uh, a series of columns change like you expect. But this other part don't. The rest of them don't. But when the other half of the key changes, then they start changing. Right? So that's partial dependency. It's good that you have some dependency, because what you want. You don't want columns doing their own thing and not caring about the primary key. But it's not fully dependent. So usually what it means is those columns have to be off in another table where they are highly synced with that primary key. Okay. So the big thing is you need a composite key, right? So if you have a one column primary key table, you don't have a second normal form issue, right? Okay. You can then jump to third normal form if you find some columns that are doing their own thing. So again, what to look for is an attribute value changes only when one part of the key changes and not the combination of the parts of the key, right? So you do have some what we call functional dependency. It's changing, but it's not. It's only partial. It's not complete. So you typically have to split the table. It could be into that one table turns into 3, typically at a minimum. So third normal form is to remove functional dependencies on non-key attributes. So what it is you have two columns that are dependent on each other. They are changing, but neither of them is a primary key. They're absolutely in the wrong table, right? That sort of thing. So functional dependencies is an important concept once we get past first normal form, right? I mean, the whole idea in a relational database is that every relational table has a primary key. It's the one that's in charge. You know, when your student number changes, the first and last name, birth date change. When your vehicle number changes, the make and model changes. That sort of thing. And so that's really important. And so here, this would be the case where you have a primary key. Most of the columns, when the primary key change, they change. But then you have like two columns off on the side that's doing their own thing, like, and that typically tells you don't belong here, right? So you belong in your own table. So if the value of an attribute seems to change based on another column, but that column has nothing to do with the primary key, right? They're just off doing their own thing. So you typically have a hidden entity, and you need to spin it off into another table. Boyce-Codd normal form. BCNF is a special case of third normal form. Every column is a candidate key, always filled in, always unique, right? Never repeating. You can take like the periodic table, right? Typically a single column primary key, right? Lots of examples. Periodic table, like I said, almost every 2-column table, you know, that we have like a coding table or lookup table, right? That's what LUT stands for. So people call them coding tables or lookup tables, where you look up some code, right? It's typically a 2-column table. One of them is a primary key, and one is some attributes. And everything's no blanks, right? Always filled in that always unique information. Nirvana, right? Of course, there's lots of hazards. It's possible to break up the original data in such a manner that the user is unable to answer a question that they were able to answer before, right? So always make sure that in the interview you record the typical queries that the database has to answer and check them against the model that gets created. So you need, you know, just like when you write code, you debug, you need to create a model, fill it with data, and see if it can, and debug it by writing queries. Query always wins, right? It can't be this pursuit of the ultimate model, right? You collect data to do something with it. The something is usually ask it questions. It has to be able to ask the questions. Otherwise, it's a lot of money that got wasted. So what I'll do now normal form walkthrough. So this is a CBEPS question that some surveying students had to take for certification. This question like this has shown up on their exam before. So you can probably search if you're curious, CBEP's previous exams in Google, take you to a page, and you can see get some PDFs. Look at the E1 is the exam that this is off of. So they presented a table and they said give examples of where you have normal form issues. Okay, so I'll get the pointer here. One thing is to look at is that you have parcel, and we don't know, but we'll assume that parcel ID is the primary key. Well, since it's a one-column primary key, right, I can only have first and second normal form issues. Now, the arrow's just showing you how I changed it. So I created a similar table, but I just did everything in lowercase and that sort of thing. And I explicitly set the primary key here in Postgres. And so, my primary key is fine, but I have issues of storing, data not being atomic. I have two owner names in here. I have two phone number names in here. And what I'm trying to do in this table is typically, there's a couple many-to-many relationships that I'm modeling. I'm modeling the fact that a parcel can have many owners, right? And although we don't have an example because they don't have enough rows, but that a person can probably own many parcels, so it's many-to-many. A person can have many phone numbers, or a phone number can be shared with another many-to-many. So this is where we get into trouble, is most fields have a blank, right? So typically, if all the rows are filled in, that row just won't exist in the database. Later on is what we'll find out. So this is a table that I made. So this is the first table I made. This is just trying to stay as close to what their original question was, but just basically all lowercase. So I don't have a bunch of issues because they were using mixed case. My second table, just get rid of the abbreviations in that, and just for myself to be consistent. So I just want you to know how I got to my table and how I rename things. But from this point on, we can start the normalization process. And so this is, again, the same data, but just with things named, right? Maybe I have OCD, but just their column names are driving me crazy. And once I got that done, okay, this is original data. I haven't done the data yet. I was just doing structure of the table. I can start ripping it apart. So one thing I can do is if I put each owner on their own row, right? That would get rid of first normal form in the owner table and in the gender table. And I still won't be able to do phone numbers yet because this is a phone number for a particular person. But to do that, I'm going to need a compound key. So I'll have to add a column, a surrogate for owner. Okay. And that's what I'm going to do here. This is good in a way because I'm resolving first normal form issues. To do that, I'm going to cause a second normal form issue, but that's okay. It's not just best, but the rule is you fix all your first normal form issues first, right? And if that causes another issue, that's okay because we'll fix that. We got to get rid of all the first normal form issues first. So I am going to add an owner ID column, and it's going to be a compound key. And we'll try to get, like I said, let's get rid of all the first normal form stuff first, and then we'll figure out how to deal with any second normal form issues if we have them. So I add a row, but I needed a column, and I got my primary key on here now. Okay, but I've cleaned up the owner name column and the gender, right? So I don't have any multi-values in there, right? I haven't been able to fix phone number, right? Because when I look at that, it's sort of a different issue, right? I'm going to have to, there's no way around phone numbers. I'm going to have to spin off another table. Because if I look at John Smith, he has two phone numbers, so a person can have many phone numbers. I see a phone number being shared, and I see a person without a phone, right? That sort of thing. So the next thing would be to tear the phone numbers off into another table, and then the relationship between them is many to many. So I'm going to end up having at least three tables in the end. So here I have my parcels table with the compound key, all the phone numbers off in their own table, and a many-to-many, which means there's going to be a table in the middle here. Okay, and that. And I'm also going to take the opportunity to chop up the phone number. I'm going to add on a country code, right? It's assumed because we're in North America, United States, Canada, that there's a 1 entered. If you're calling another country, there are different numbers for those particular countries. There's an area code, a prefix, and a line number. Some people call that the exchange number, like the last 4 numbers. Like at BCIT, if you want to phone someone, you just put in the last 4 numbers of their number, and it calls their office phone. You have to put the whole thing in, right? For I guess ease or ease in that. Now, if we take a look, right? So we've ripped off the phone numbers and chopped them up. Right, so we have a primary key, we have the country code, area code, prefix, and line number. Now, since these are numbers, I'm not too worried. It is repeating, so I might have some issues. But as I fill this with more numbers, I might notice that area code isn't repeating too much. But BC has 604, 250, right? 250 in that. And so sometimes you might go, well, do I spin off another table to handle that? Well, you might be able to, and you may not, right? All depends. There may only be so many area codes in Canada, right? And that. And so I'm not here to solve the world's problems. For me, I'm going to say that's chopped up enough. I don't want to chop it up anymore, right? This is my many-to-many table, right? 2-column primary key, right? So there's a little bit of nirvana there, right? 2-column table. Everything's a primary key, which means it's filled in and unique. I might have got a little Boyce Codd normal form on that table right there. So, and then I have my top one. So I'll say that my bottom one, first normal form, as far as I want to take it, right? And I won't have any second normal form issues because it's a 1-column key. This is a 2-column key, but they're all primary keys. Right? There are no other columns that could have partial or no dependencies because I ran out of columns basically. So I'm going to say those 2 are done. And I got to go back up to the top one and ask the question. Okay, does this have any first normal form issues? Right? And let's say I got to a point that, okay, no, it looks clean in terms of first normal form. Then I'm allowed to ask the question, do I have second normal form issues? So do I have columns in here that seem to be synced with parcel ID only? And do I have columns in here that are synced with owner ID only? And the fact that a parcel is, a lot on the ground and the owner is a human, well, I already intuitively I know that's 2 different things, right? And I know area isn't probably the area of the person, it's probably the area of the lot, right? And I know that city is probably the city that the lot is in, and that the house number is probably part of the lot again. And the fact that Jack Brown, those probably belong are the first and last name of the owner, right? And that the gender is probably the owner, not the gender of the lot, right? So what it means is I do have second normal form issues in this table that I should probably resolve. And so this is parcels, our original table, and our phone number table. And what I'm going to do is spin off or tear apart parcels and owners, but it's a many-to-many, so there's going to be another table. So in the end, I'll have 1, 2, 3, 4, 5 tables in my schema. And so here I've ripped apart the data, right? And so house number, area, street name, city are now just associated with the parcel ID. And it seems to be, for the most part, okay. Phone numbers, I said, was done from last time. And what we need to look at here is owner. So owner, first name, last name, gender. That seems to be all stuff about the owner. So that looks looking pretty clean, right? And let's say, well, how are my tables doing now, right? And so because I have two tables with two columns as primary key, right, but no other columns, so they can't have second normal form issues, and they can't even have third because, like I said, I'm out of columns, right? Phone numbers I said was done from last time, so I'm not going to break that down any further. And then the question becomes, do I have any third normal form issues in here? And so we had to find a column that doesn't seem to be changing when the primary key changes. And the one that pops out kind of is Ottawa, right? No matter what the primary key is doing, Ottawa, Ottawa, Ottawa. And this is the word Ottawa typed in 3 times, right? So that means someone's actually typed that in by hand. And so the question might be, well, if that column's off doing its own thing, then I just spin it off into its own table, okay? And so I'll spin that off into a cities table, right? Now, because this is a one-to-many, I don't add 2 tables, I'll just add 1. And so now I'll put a foreign key in here, right? And this is the thing called controlled redundancy. This is allowed to repeat because it's a number that links to this table. And then if we ever, decide to change the name of Ottawa, we've changed the names of mountains and stuff like that. So one day it might change, right? Someone might look up that word and find out, ooh, it's a bad word. We're not allowed to use Ottawa anymore. And so we have to change it. But in this case, we just go to this one table and change it once, and we're done, right? The other one, we'd have to go to every place where it's typed in and update as well. Now, here's a good question. What I did with Ottawa, can you see another example on here of that? I believe that there is, but then it's up to you. How far do we want to take this, right? Because eventually we got to get on to the task of writing the queries to answer a question, right? That's why we have the data. So I'll let you, I'll challenge you to find one more thing to fix, right? And you can ask about it on the discussion boards. So we're going to be into some extended time here, have some fun, right? Talk about some design traps and other issues. There are some types of traps or things that can go on. I'll update that title, just issues. Well, whenever you have a one-to-one, right, that's primary key to primary key. It's the same primary key. Did you just arbitrarily chop an entity in half, right? Why is it one-to-one? There is a special case of one-to-one called subtypes, and so that's understandable. But did you just arbitrarily chop an entity in half, right? Because they're using the same primary key. Are they not the same thing? There's a chasm, and that gets into participation where you didn't enforce participation, and so you do a query and no rows come back. Never fun. Fan trap is the previous Curtis model where too many rows come back, right? Just because what you typically have is a many going into a one and a one going back out to many. So the reverse of a many to many, and so that's called a fan trap. It fans out and picks up more rows than it should. And redundant relationships. So if you actually have a loop, like you can see a loop with the relationship lines, or something gets closed, right? Then that means you have redundant relationships. So always challenge one-to-one. Why would two entities have the same PK? Are they not the same thing? So like student number, well, that's the student. This should just be in the student table, right? Why are parts of you in one table and other parts of you in another table if the student ID is about you, right? And again, like I said, where they make sense is subtypes. You can have a chasm issue, right? Participation is not mandatory, and you want mandatory at least on one side. Child, mandatory relationship with parent, right? What do you see? No rows coming back when you know there should be some. Fan traps, right? Look for many to one, then a one to many. right? Not a many to many to one, right? Those work, right? Those are classic many to many. They behave, but when they're flipped, that's when you can have problems, right? Depends on the data. Too many rows, unrelated rows are returned, right? So in the previous, earlier in the course, I think of Mod 2, where I have a video of a fan trap and actually taking a look at the Curtis model with data in it, and we ask the question, who's hunting? And we get all these other companies back that actually aren't hunting, but just because they use the same site as the people who are, they get tagged as hunting as well. So that can make the relationship ambiguous because you said they were hunting when they weren't. This example right, your textbook of a fan trap. Do you notice how I said it's a many going into a one and then a one going back out to a many? And in the Curtis example, which we'll demo, more rows come back, right? Because they were at the same site, and it's one site going back out to many. So there are ways to resolve that as well, but it depends on your data, right? The resolution on the Curtis one was coming to terms with the fact that you need three things to be happening to figure out what kind of usage was on a particular activity. So here's the Curtis model again, and this is where we have our many coming into one going back out to many. So that's the table that causes the fan trap. When we again had this compound key that it was a particular company at a particular location on the ground doing a particular activity that led to a usage level, then we were able to actually properly structure the data, reload it into the system, and it could start answering questions again with proper results. What you could do now is pause this audio lecture and watch the demo. So what we'll talk about now is redundant relationships. So we need to remove them. Again, what to look for is a loop. Each pathway needs to describe a different relationship. They could be valid and have to stay. They can cause problems. Here's an example. We can see the loop here. I can get to player down this path or through these tables. And the issue might be is if you get a different number of rows coming back, it means you're getting a different answer depending on how you do it, right? It's always better to have one way to do something, right? Because if it produces different results, then you're not as confident in what the answer is. I'm going to switch gears here and talk about subtypes. So there are these terms in subtypes. You'll see something called a supertype and the subtype, a subtype discriminator. Which subtype are we talking about? And then constraints on whether subtypes overlap and if subtypes are partial or complete. Now, there is a diagram that you can take a look at, but it's best to watch the video where I go over those subtypes to clear things up. So at this point, you can pause this audio presentation, go to the Google Slides version, and then click on the link to the video where I explain how the subtypes work with a real-world example. So we'll talk a little about stories in the field. Of course, you've seen the min file number, data I've worked with, one big table. That's how it used to come in. We have to tear it apart in order to use it. Large mammals, when we were tracking or trying to do inventories on ungulates, specifically mountain goat, it used to be a lat long and a big comments field, right? And that. Curtis I've talked about, broken queries with the fan traps, and even we did another one with flood boxes, and definitely some hidden entities, and the fact that we were mapping parts versus the whole. And so that can get into an issue. So there are these like flood control structures, and they can have different gates on them and different pumps. And it wasn't until I went past one on 176th Street by Fraser Highway that I realized what we were mapping was the parts, not the whole. So there's this flood control structure, big pump station, has all these different types of pumps and that to pump the water from one side of the dike into the river. And so there was lots of cases when we were just mapping pieces at this flood control structure. It does, I mean, it's interesting cartographic problem, but you know, because you think these are all sort of separate entities, but they are part of one big structure in that. And so that's very interesting. So what I'm going to, because I've talked about the min file number and Curtis a lot, I'll talk a little bit more in detail about large mammals. So here we have goat flights, and so this is the old goat flight sheet here. It wasn't even a table. I mean, it was a piece of paper that was faxed into us, and we'd have lots of them. All so these would be the actual pieces of paper they had in the helicopter on a clipboard. So there was a lat long written down that they saw on the output of the helicopter, and then they wrote a comment. And when we looked in that comment, there was a lot of stuff going on. One thing we noticed was that they were tracking more than just mountain goats, right? Every once in a while you'd see cougar and bear and this other in there. So we had to have a species table. And there were species codes that we had to use that FRBC had sort of already spec'd out, so official species code. There were comments about when they saw a goat, if it was in, what kind of habitat was it in, right? It's a W1 through 3 classification. And that, and so that was another table that had to be created, right? All the points were of a particular flight, and that flight was done in a particular area: Sunshine Coast, Squamish, Chilliwack. There was a person who was the flight recorder, which could, again, that's not shown here, it could be another table of flight, people who are official, like the forest ecosystem specialists who are actually up in the helicopter, right? A district code, what district are we talking about? Chilliwack, Sunshine Coast, all that kind of stuff. The date the flight was done on. And then there's individual point locations, right? The lat and long and that. And although this is tailored specifically to mountain goat or ungulates, right? Because what they were after, but they could have had what we call an incidental wildlife observation, which they were supposed to record according to the regs. That's why there's other species here. But if it was a goat or a group of goats, then they would try to determine how many males they had, how many females they had, how many sex unknown, how many adults versus juveniles, how many age unknown. And it's not in this table, but they even tried to say how old they were by the number of rings on their horns. So they would try to guess at that as well. But from that piece of paper and a comments field, all this other information was actually embedded in there, right? Lots of many to ones and stuff. And this isn't the complete model, because like I said, the flight recorders is another table that could be in here as well. But sometimes that's what we find when they have a big comment field, is all this other information. Because of all those sheets they faxed in, they said, can you tell us how many total goats we saw this year? And we were like, not on those sheets, but once we got it organized in the tables on the right over here, we were able to answer that question for them. So we'll do a summary here and wrap up this lecture. So when we're talking about subtypes, we're talking about completeness constraint. We talked about design traps like the fan trap as well, and that disjoint subtypes, whether they're overlapping. We talked about some extended ER modeling as well. The Curtis resolution, where we have those three things happening on the ground, is an example of an entity cluster. Right. Talked about subtypes and supertypes in the video. Right. The fan trap and that. Subtype is an example of, is one way to do inheritance in a database, in that although inheritance and generalization are usually software object terms, those are tied to the subtyping concept in extended entity relationship diagramming. Right. Natural key we've talked about before. Overlapping subtypes is the, if you're not disjoint, then you're overlapping, and if you're not complete, you're partial. Right. And that. And the whole concept of subtype is where you're specializing, right? You have a more generic thing, supertype at the top, and the subtypes are specializations of those particular subtypes. Surrogate keys we've talked about before as well. Okay, and so we'll leave it there and conclude. If you need to re-examine a topic or need clarification on a term or concept, or just have a question, you can get an answer by posting a note on one of the discussion boards for this course. This concludes this lecture.